Okay, so I will start by giving only a general background on what this webinar is about. So this is the LiveTalks series by EuroStruct. It is a series of webinars where we invite experts from both the academia and industry to share perspectives and exciting findings on their work that relates to the goals of EuroStruct, the European Association on Quality Control of Bridges and Structures. Within the past, actually more than a year or so, we have hosted different seminars that go over topics of relevance both in Europe and in the US, covering building information, modeling, standardization aspects, structural health monitoring, and data-informed safety assessment of transport infrastructure. And today we're particularly pleased to have an expert who will discuss the topic of corrosion. I will soon give the floor to my co-moderator to introduce Sylvia. Before I do that, I want to mention that I will be moderating this series together with Maria Pina Limongelli. I am Eleni Hadji. I'm the chair of structural mechanics and monitoring at ETH Zurich and a member of EuroStruct, of the EuroStruct Association. Maria Pina Limongelli is a fellow expert in the domain of structural health monitoring, professor at Politecnico Milano. And we invite you to gather your questions as we go about the talk that is about to start in a few minutes. Sergio will be transferring these questions to us, and we will organize them so that we can transfer them to Sylvia in the end of the session. So it will be a moderated talk in this respect. With this, I will give the floor to Maria Pina, who will introduce today's speaker.
Thank you, Eleni. It's really a pleasure to introduce Sylvia Kessler. She's a professor of engineering materials and building preservation at the Helmut Schmidt University of the Federal Armed Forces at Hamburg in Germany. She has a master's degree in civil engineering and a PhD from the Technical University of Munich. Sylvia has over 15 years research experience in durability and service life design of reinforced concrete structures with special focus on reinforcement corrosion, which, as you know, is the topic of the talk today. Her research activities also include the non-destructive evaluation technologies for testing and monitoring, condition assessment, and rehabilitation of concrete structures. Among other several activities, Professor Kessler is the convener of the FIB Task Group 3.3 on existing concrete structures, life management, testing, and structural health monitoring. And she also chairs the RILEM Technical Committee on assessment of electrochemical methods to study corrosion of steel in concrete. So I think we can all agree that Sylvia is really the right expert to discuss this very interesting topic of the webinar today. And with this, I think I can leave the floor to Sylvia.
So thank you very much for the kind introduction. It's my pleasure to be here, and it's also my pleasure to give the talk on reinforcement corrosion of bridges, mechanism, assessment, and rehabilitation. And since our time today is limited, I would like to focus more on the assessment part, which I assume is probably the most interesting part for most of the audience here. So if you look at our bridges, not only just in Germany, just around the world, we have normally the typical life cycle from the design to the execution over the use phase. We probably have also repair, which needs to be done in order to ensure our service life, another use phase. And then we have to think about the demolition and the recycling. And now, since today the topic is reinforcement corrosion, the question arises, when do we are really concerned about corrosion? When do we think the first time really about corrosion? I would assume, perhaps it's a little bit offensive, I would say you think about it first in the use phase, just when you start to see it. For example, here I have some very nice pictures from an existing concrete bridge. And here we have very typical signs of corrosion, which we see directly. We have here the rusty spots, or at least a typical brownish color here on the structure. And even worse, we see here spalling. We see the reinforcement, which is clearly corroding. And here a closer picture. Now you're thinking, are we still safe? What is really the condition of the structures? But is it the right time to think about corrosion? We need to think about it much earlier, as already in the design stage. But what do we do normally? We are a little bit, how to say, used to just apply the exposure classes according to the Eurocode. And we know that we have a certain service life that we need to ensure, and we have a certain condition. And during this design stage, we think, okay, we have our service life. Let us apply just the exposure classes. And since we talked today about reinforcement corrosion, we have only to consider the XC, XD, and XS. And for those who are not familiar with the Eurocode, since I'm talking today from the perspective of the Eurocode, this class is concerned about carbonation-induced corrosion, here about de-icing, or the ingress of de-icing salts, or the ingress of salts from the marine environment. And we are very used to it to choose just the concrete composition or the concrete cover depth, which is assigned to each exposure class. This is how we do it for years now in Europe, and we apply it, and we do not think about anymore on corrosion. But to ensure at least a minimal nominal condition, we do not really know. The exposure classes tell us nothing about a real service life. We cannot say what is really the availability of our structure, what is really the service life, and we have no idea how the condition behaves over the time. It would look like this, then we are safe because we will achieve the service life until the end of the design service life, but it could also look like this or like this. We do not know that. The descriptive durability design will give us no further clue. What we could do is we can apply probabilistic models in order to estimate our reliability or failure probability. And every time, if I will talk today about failure probability, it's always meant corrosion probability, so the probability of reinforcement corrosion. What we did in Germany, at least we have a very, or at least I used as background information for all the probabilistic modeling, because I do not want to go into detail during this talk. You will find as FIB, especially the model code for service life design or the model code 2010, and you will have some more further information in the more recent Bulletin 76, which supports you if you would like to do your probabilistic modeling yourself. We had a project going on just in Germany, and we would like to consider what are really the exposure conditions we have in Germany. So on the northern part, we have the seas, the marine environment. So here we have really to be concerned about chloride-induced corrosion. And in the south part, we have a lot of snow, harsh winter times, and here also a lot of de-icing salts are applied on the streets to ensure the traffic safety. And we looked what are the typical stresses we have with regard to corrosion. And we compared this to the material resistances which are allowed according to the Eurocode. And the result was kind of surprising. If we just consider now, and here's a reliability index, the beta value you can see here over service life about 100 years, we just calculated for the X4 exposure, which is the most severe exposure when we have to consider carbonation of concrete, which could lead to reinforcement corrosion. And here we have the range of the reliability, which is very broad. So here on the upper line, you see probably the most severe environmental actions with regard to carbonation. The less severe, sorry, the less severe. Here we have the most severe. And here we have the poorest material resistances. And here we have the best materials resistances, which are still in line with the Eurocode. So we have a very broad range of reliability. But if we check what it's normally a limit state, which is normally a better value of 0.3, we say that we can easily ensure a service life about 50 years, and there's only a very low probability of corrosion if you would like to ensure a service life of 100 years. So if you apply them accordingly, appropriately, you will probably do not have any issues with carbonation-induced corrosion. As the next step, Because normally, if you have a reinforced concrete structures, which is assigned to the exposure class XC4, especially for bridges, it's normally as well XD3. And normally, so since XD3 have harsher material resistances, or you have to build a better concrete, which has also normally better resistances against carbonation. We also checked that for the XC4 exposure, but under the boundary conditions that XD3 is also valid. But nevertheless, since now we have much higher material resistances, here we do not have to concern at all that we will have problems with carbonation-induced corrosion. But at the end, the most important thing is what's going to happen with the XD3 or XS3 exposure. Under this exposure class, we normally have cyclic wetting and drying in combination with the exposure to chloride ions. And this is the most severe environment you can have when you are concerned about reinforcement corrosion. And you see that the scale of the reliability index has already changed. And this is the range of the reliability you can get just applying the Eurocode exposure class rules in order to ensure normally a service life about 50 years. And you see here now, this is a normal limit state, the reliability index of 1.3, and which is equivalent to more or less 10% of failure probability, so 10% of corrosion probability. And looking at this diagram here on the right-hand side, and if you are in charge or an asset owner of bridges, you need to be concerned about reinforcement corrosion. This is so likely to happen, especially if you have exposure class XD3 or XS3. So you have to face reinforcement corrosion with a very, very high probability. So we're concerned that our prescriptive design rules, durability design rules, are not able to ensure a repair-free service life, which they should. Hopefully, we will change very soon our prescriptive durability design rules to the load lab performance durability design rules, which is already on a preparation. So we have very high corrosion probability, and this means that we have to concern, especially during inspection and monitoring, about what kind of methods we can apply. So what is really the mechanism when we look for reinforcement corrosion? You probably have seen the 2D diagram several times already, so that we have the initiation phase and we have the propagation phase. And the initiation phase ends with the depassivation of the reinforcement. And here I bring you some comparable sketches, because normally the concrete provides a high alkalinity, which leads to the formation of a microscopic oxide layer. And with this passive film, we call it as such as well, we have corrosion protection. Now we have two mechanisms, which we already heard from the exposure classes. We have the carbonation, which leads to the process that the alkalinity got lost, and the microscopic oxide layer, which normally prevents corrosion, dissolves. And so we have a depassivation. So the steel is able to corrode, which does not mean that the steel will corrode. So other boundary conditions has to be fulfilled. And for the more severe condition, so we have this concrete is still in an alkaline condition, which is often forgotten. It's still alkaline. But we have also chlorides in our system, mostly from sodium chloride from marine environment or from de-icing salts. They penetrate through the concrete until a critical threshold has reached the reinforcement level, and there the microscopic oxide layer will be destroyed locally. So here we have the typical corrosion, which leads also to the depassivation of the steel. All these processes will take time. So this is something what we can see in the 2D diagram as well. But what is really the difference between both mechanisms, so the carbonation-induced corrosion or the chloride-induced corrosion? Normally, we have a very homogeneously distributed depassivation of the steel, so very uniform corrosion, whereas in chloride ingress, we have it very locally, as I mentioned before. And this means that looking at the anodic partial reaction and the cathodic partial reaction, this will take place on typical different locations. Here, it's very distributed very equally over the whole reinforcement, whereas for chloride-induced corrosion, we have a concentration of the anodic partial reaction leading to the typical pit, which leads to other complications for the structural engineering. And here I promise this is the last chemical equation you will see today. So what I normally do for my lecture, we place a normal reinforcement just in a solution with a pH of 12, so comparable to the steel. Here you see the sketch, so the water still have colorless, it's colorless, so there was no corrosion product as well at all. From the carbonation, we place just a reinforcement in a solution with a pH 8, which is comparable to carbonated concrete. And here we see the brownish color, so a lot of iron oxide has been produced, so the typical rust. And for chloride ingress, here we prepare normally solution with a pH of 12, and we add sodium chloride to it. And here we can see some iron oxide products at the bottom of the container. And soon as we have corrosion, we have a flow of electrons, and which you can measure easily by a current. Sure, if we do not have any corrosion at all, we won't have any current. Now for the carbonation, here we measured the current as well, and we ended up with 0.36 milliampere. Now you can think, do we really need to be concerned about a corrosion current about 0.36 milliampere? Especially since it's just a current, normally we have to calibrate it against the area. So in order to have a corrosion current density, is it really a lot? Is it not? What does it really mean if the structure still have to serve for 30 or 50 more years? And what would you assume now, and think about what would you assume now for corrosion current for chloride-induced corrosion? Do we have any experience? Guess a number, and I will show it directly. Here we have a corrosion current about 7.39 milliampere. 7, much higher and much more concentrated just on the pits. So if you would like now to assign it just to the surface, you have here a much higher corrosion rate. And this is normally what we see also on site. And this is a typical example here on my next slide. This is a reinforced concrete bridge. I took this photo in 2016, and this bridge was built at the beginning of the 80s. So it was quite a very young bridge, and you just see, and you're probably now very happy if you're not the asset owner of this bridge, and you already plan to rebuild it totally. So now we know what leads to the passivation, but now the other boundary conditions have to be fulfilled in order that corrosion can start. So we need the electric conductivity of the steel, which is typical, what you cannot prevent at all. All reinforcement normally is electrically connected within a reinforcement structure. We know that. We need a certain ionic conductivity of the concrete, so there must be a certain moisture in the concrete, which is normally for bridges, which are exposed normally to the weathering, no issue at all. We have normally a sufficient iron conductivity. We need oxygen. Normally we have enough oxygen, and we have a certain driving potential. And normally all these 5 requirements are fulfilled easily. So probably for bridges, or the very high probability for bridges, as soon as we have deep passivation, we will also have initiation of corrosion. And keep in mind, all these 5 basic requirements needs to be fulfilled at the same time. If we could, or if we are able to exclude one of these basic requirements, no corrosion can take place. And this is just a clue on how to repair the structures and how to prevent ongoing corrosion. So next step, I come back now to the 2D diagram. Now the next step, as soon as we have corrosion going on and iron products, iron oxide are produced, they need a much higher volume, which leads to stresses in the concrete. As soon as all the pores in the concrete are filled with iron oxides, and the more iron oxide is produced, very easily the tensile strength of the concrete is exceeded, which leads to the concrete cracking, and afterwards to the concrete spalling, to the loss of bond, and to the loss of the cross section. Here on the right-hand side, we see now a picture, which I also like to show normally in my lectures, because here you see all the different steps for all the different damages of corrosion-induced corrosion damage. Here you see the concrete, the corrosion cracking. So you see the very clear crack, you see the brownish color coming out of the crack, which gives us a hint that here's iron oxide, so corrosion is going on. You see here's a spalling, you see the loss of cross-section, and follow here's a shadow, then you can see that here's a reinforcement, it's totally missing. It has been gone due to corrosion. This picture is from a very, very old concrete bridge from the 50s. And you see very nicely how all these different damage situation looks like. And just from the point from depassivation to concrete cracking, here it's the most difficult point to guess in which condition our structure is, because corrosion is not visible. If we do not see any cracking, we have no chance to assess corrosion just from visual inspection. This is a critical point where you do not know, is my structure corroding or not? So coming back to the life cycle, now we have understand the mechanism. Now we also know that probably the descriptive durability design rules of the Eurocode are probably not the best way to ensure it. We have just another issue of the execution, because all the exposure classes design and all the probabilistic modeling relies that we have a perfect concrete, a crack-free concrete. We know that due to execution, we can have some problems with shrinkage, with any other issue which leads to cracking. And here I want just to mention any cracking, entry concrete cracks would enhance this process of corrosion initiation and would just shorten the surface life much more. But now we're at the use phase, and we know that we have a certain stage or a certain time where we do not see the corrosion. So what can we do? We have here now, once again, the time over the corrosion. And sure, we need to inspect, and we need to inspect frequently in order to get the chance to see how the image is developing over time. We have also monitoring, which you can do continuously, even so that corrosion monitoring is not so established. We have sensors available to do corrosion monitoring, and I hope it will increase much more in future. But currently, I know very, very few bridges where corrosion monitoring is applied. So the question is, as I already mentioned, is there corrosion or not? How can you tell so? And if you're sure that there is corrosion, which extent? Here, for example, I can show you a picture of a different structure. This is a abutment wall with a length about 12 meters and 5 meters high, which was located in the city center of Munich. More than 45 years old. It's a time in inspection, and you see nothing from the outside. And to some other maintenance issues, they also started to do a corrosion condition assessment just occasionally, not by intention. And they ended up with looking at the reinforcements. They had to do a total repair, because with a closer look on it during the repair, you see serious loss of cross-section due to corrosion. We have seen nothing from the outside. The abutment wall more than 200 meters long on both sides of the street, and you have seen nothing. So what could we do, or what did we do during this inspection in order to check the corrosion probability? The main question which you have always, if you would like to perform a corrosion condition assessment, you have to ask yourself when you should do that. Because we have also annual changes or seasonal changes. Do it more in winter time, do it more during summer. When should you do that? In which frequency? Every year, every 3 years, every 5 years? What is sufficient? What is the objective? What do you really want to know? That depends also on in which state. If you're still in the initiation phase or the propagation stage, so this will probably change the objective of your corrosion inspection. Which parameters are of interest? Which method can be applied, and are these methods reliable? And you have also some further guidance here on the FIB Bulletin 59, where we just compiled or we tried to answer some of these questions. So here I would just give a very comprehensive overview what is possible. Here again, we see the damage over the time. We know that we have an initiation phase. We know that we have a propagation phase. What we do not know is here in the interface. We probably have no clue if we are still in the initiation or we are already in the propagation phase. And what we always should do, even so at the beginning it doesn't give any clue, we need to do visual inspection. And as soon as we see anything like cracks, we need to involve a structural engineer see to be sure that the reliability of the structure is still in a good shape. It's the very beginning. What is really helpful? What kind of parameters the data? Always the concrete cover depth, the chloride content. So you make a chloride profile. You can also measure on a structure the critical chloride threshold. It is very uncommon because the procedure is quite new, but the procedure now is possible. And the carbonation depth. These are the most important parameters, and you have to do, or you have to destroy very slightly your structure. You need to at least drill a borehole to get the powder for the chloride profiles. What do you do with the data? Out of the chloride profile, you can get the surface chloride concentration, the apparent chloride diffusion coefficient, and you can also clue about the convection zone. And this information enables you to calculate a priori corrosion probability based on the model from the model code for service life design. And you know much better what is really the corrosion probability or the depassivation probability of my structure. This is something, these are all inspection methods which are very easily to do. The chloride content for this specific parameter, there's also monitoring available. As the next step, if you know now that your corrosion probability is probably or has increased, you could apply the half-cell potential measurement. This gives you data, this gives you information. Also, it's an inspection method which gives the indication of corrosion probability and not. And I will later on show a case study how to deal with this data, because you can apply the Bayesian theory in order to update your a priori corrosion probability with the half-cell potential measurement data. And this gives you very, very valuable information about your corrosion condition, not only time dependently, but also with the spatial variability of the corrosion situation on your structure. As soon as you know that you have a really high corrosion probability of the over 60, of this over 70%, now we would be probably very happy if you would have a model in order to predict the corrosion cracking time. Unfortunately, there are some models available in literature, but there is not this particular model which is validated and calibrated, which everyone can easily apply. This is still in a research state, and we have also some research going on. So unfortunately here I cannot give any further advice today, but perhaps in 5 years we hopefully will hear a model which I will be happy to present here as well. As soon as we know there's corrosion going on, very important parameter is the corrosion rate or the concrete resistance, which gives us also a clue on the corrosion rate. So because the corrosion rate can be easily transferred to the loss of cross-section or the loss of mass due to corrosion. And this is also very important input parameter for the modeling of concrete cracking. And certainly we know that at next we see cracking, and that's the reason why always the visual inspection is of importance that we need for updating. If you're still in the cracking phase, or we're already in the cracking phase, we should do the visual inspection. And have several, the corrosion rate and the concrete resistance. These are also both models which you can do as testing and as monitoring. And here we have several sensors available on the market, which you can easily apply on your structures as embedded sensors on your structures. So we have several inspection methods. We have several monitoring methods, which you can apply to get a really good knowledge about the corrosion condition of your structure. But unfortunately, the most common inspection, which is only done, is the visual inspection. But it's a pity that we do not apply all these beautiful methods because it gives us such important information. Now I want to proceed with a case study that's here all the overview comes to life. And here I just want to come back to my abundant wall, which you have already seen beforehand. Just as you do at the beginning, you start your probabilistic modeling to get an idea of your a priori depassivation probability. And at the time of inspection, the structure was more than 45 years old. And here we have a depassivation probability for this particular structure of 30%, so corrosion probability of 30%. It's quite high. This was the reason why we decided to do some further inspection. Here, these are the results of the concrete cover. The concrete cover is slightly higher, as you would expect, keeping in mind the design codes at the time of construction. And we recalculated the depassivation probability with the current concrete cover depth measurements. And we could see that, and now I'm sorry for that. And now you see that the depassivation probability decreased because we have a much higher concrete cover depth than expected, and now we have a corrosion probability of 22%. Now you think 22%, is it high, is it low? So something you have to decide for yourself. Here the asset owner decided it's a little bit too high, so he did some further inspection, and as I mentioned, the half cell potential measurement, which I would like to explain very briefly, gives you just the information you need to know. Here you need to connect your a voltmeter with a reinforcement, so you partly have to destroy the concrete in order to get the electric connection. Then you have a reference electrode, which measures the half cell just in between the reinforcement and the reference electrode. And as soon as we have a corroding spot here, the potential is much, much lower than at the cathodic areas in the neighborhood. And if we now scan the whole concrete surface, not only with a rod electrode, as you see here, but with a real electrode you see here on the picture, you can easily scan huge surfaces in order to get the information about the half cell potential. And this is the only slide where I bother you with some German. These are now the equipotential plot. It's normally the representation of any half cell potential measurement. You see here that the potential, and normally, as at least according to the German specification, we look at the spots with the most negative potential in combination with a pronounced gradient of the potential. So here I would guess I have here a certain corrosion probability here as well. But what does it really mean? How can I quantify this data? And now we need to apply the Bayesian theory, which you probably, most of you are very, you probably know very well. But normally we have the problems that we cannot apply it so easily due to the fact that this information, the likelihood that the inspection quality independence of the structure condition is not known, or that the inspection quality, so that we mostly do not know what is the probability of corrosion given the condition of the structure. Here, for this particular issue, I did some investigations before, but first we have to think about what kind of situations we have for inspection in order to get this data. Here we have a qualitative test method. At the end, we will end up with the outcome, is there corrosion, yes or no? We have no quantitative value. We cannot use the half cell potential itself. It's not an absolute value. We have to evaluate it qualitatively. So normally, if you have a defect-free structure and we decide that it's defect-free, so corrosion-free, it's okay. So we have no costs and just costs for the inspection itself, but the asset owner can be happy. If we have a defect and we detect the defect or we detect corrosion, it's okay. We have repairing or destruction or cost for testing. Here now comes the much more severe situation. We have no defect, but we detect the defect, so we detect corrosion, so unnecessary repair. And the worst case would be that we have here corrosion going on, but we do not detect it, which could lead to very severe consequences. And we all of us, we probably know some structures which collapsed. If with due to corrosion or not, is something we probably will never know, but hopefully none of us will be in this situation. What can we get out of these kind of situations? We need now the parameter, or we have at least this kind of signification and indicators. Now here, to see what we call a hit or what we call a miss. And both the hit and the miss leads us to the probability of detection, which is just the likelihood we need to take for the Bayesian, to apply the Bayesian theory. The other one, the false alarm rate, we do not need any further. not now, but for, perhaps there will be also some useful application for this parameter. Here I want to focus much more on the probability of detection, so the probability of corrosion detection, especially for corrosion detection. Here we did a very comprehensive evaluation of that, but I would slightly skip a little bit about the slides, having in mind the time. I think the most important slide is probably this one. We have here the probability of detection, independence of the defect size, which is in case of the corrosion, the anodic area, just the area on the reinforcement surface where the anodic partial reaction takes place. And we have different grid sizes, so the scan size of your electrode, and you see that the probability of detection decreases with increasing grid size. This is typical. This is something which you would expect probably. And now we can take this data to apply the Bayesian theory. So we are now able to just have the information about our likelihoods. Here, this is also part of the evaluation from the slides before. So here we took a grid size of 25 to 25 square centimeter, which we did on the structure, and we assumed a concrete resistance of 400 ohm meters, and then we will be able just to define our values which we need. And by applying first time the Bayesian theory, we can tell now, as soon as we indicate corrosion by the half-cell potential measurement, we know now our corrosion probability increases from around 22% to more than 60%. And as soon as we do not indicate corrosion from the half-cell potential measurement, the corrosion probability decreases slightly. So now, look here at the spots. Now we have here very high corrosion probability, or we have a very high indication, I would say. Then we could here derive that we have a depassivation probability of above 60%. Now you need to be really concerned. The 60%, I think this is still a lot. We can also work further the real data, which we see here. We do some statistic analysis, and here I do not want to go into detail too much. This is also published here in the conference paper you see beneath. And later on, we are able just to transfer here the half-cell potential measurement directly into a corrosion probability. So this is a failure probability, corrosion probability. Now you really get a clue. You have a quantitative evaluation of the corrosion condition assessment of your structure. And you can easily see where you have a really high corrosion probability, about 80%, and which parts are not do not show a corrosion indication at all. And with these data, you can really work for further inspection, can work for this for further repair, and you have quantitative values. But nevertheless, here we had the chance to look also on the reinforcement itself due to the total repair of the structures, and you see here again just the same information you saw on the slide before. And on the diagram here, I want now to show you the truth, just the parts where we indicated loss of cross-section. So where we have a clear sign on the reinforcement itself that corrosion was going on. And we just compare, if you just compare both, you can see here that it was a very good agreement between what we predicted as a high corrosion probability and what we had really as signs of corrosion at the reinforcement itself. So I'm really in favor of this method. This gives us really quantitative data on the corrosion condition of structures. So this is just a case study, and I want to move on because we have still to talk about one or two phases more. And I would like to continue for the repair, but please keep in mind also, I would also like to look on the watch, and I would to keep it short for the repair. Here, I want to come back on the basic requirements. Keep in mind, you have to exclude one of it just to prevent corrosion. The easiest is that you prevent the iron, that the possibility of iron dissolution due to carbonation or chloride ingress. So you have to exclude the chloride, or you have to exclude the carbonated concrete. So you do a total replacement of your concrete. You can also apply cathodic protection systems, which excludes the driving potential. It also excludes the possibility of iron dissolution. Normally how you proceed, you need your condition assessment, which we have seen the slides before. So you need to know the cause of the damage. It's easily, we just talk about reinforcement corrosion. What is really the objective? So how long is the remaining service life of the structure? Is it 10 years, 20 years, or 50 years? This makes a difference for your repair. What is the repair principle you would like to follow, the repair procedure, and what kind of material is appropriate in order to fulfill the repair principle. We have different options. You can do a total concrete repair, also replacement. You can do concrete coatings, and you have to do it several times normally, or you apply a cathodic protection system. You have different options. You just have to think about when to apply it and how often you have to do it in order to achieve the remaining service life. There are plenty of more options, but just to have a first view on that. Here again, I want to skip a little bit the slides with a look on the watch. And I want also to discuss very shortly one additional parameter which we haven't touched yet. Because if you look now here on all the different limit states we have to corrosion, and we also probably very familiar here in this audience about key performance parameters, we know that we have, due to different damage situations here, reduced resistance, which affects our reliability, which will affect directly the safety of our structures. Then we have probably a limited availability. And as soon as we have to apply repair, we will definitively have costs, and sure, we have an impact on the environment. And here I want just to focus, just want to show here on the next slide, what is really the impact of the environment in comparison of the most popular inspection methods, I would say. Here we have just a concrete repair, so total replacement of the chloride contaminated or the carbonated concrete in combination with the cathodic protection system, where you apply here an external anode, you establish an electrical connection, and then you just apply a current from the outside to prevent the reinforcement to corrode. And you would guess, cement, concrete has such a high carbon footprint. And now think about which of those methods you would guess has the poorest carbon footprint. And then you will probably be surprised, because here we wanted to ensure a service life of 75 years. And we compared the global warming potential with the cathodic protection system, with the concrete repair system, and at least with 3 indicators of the sustainability indicators, the cathodic protection ended up much worse with this carbon footprint than the concrete repair. So keep in mind, always cement must not be the less sustainable. The problem here with the cathodic protection system is that you need a lot of electronics, and you need to replace very often the electronics, and this gives huge impact on the carbon footprint. This is only a sidekick to the corrosion condition assessment, and here I want to mention more durable equal to more sustainable, and I have to say not necessarily. We did several studies on this issue, and we have some projects going on in this field, and we can say that, as I mentioned, even so that you see very often that the people argue with more durable must be more sustainable. No, have a further look on it. As you can see, probably due to the comparison of the concrete repair with the cathodic protection system. And now we at least completed the whole life cycle, and I just want to mention, we need to think about the corrosion just from the beginning, just at the design stage, especially if your structure is exposed to chloride, which is the most severe exposure you can have with regard to reinforcement corrosion, and do not think about it just at the use phase. Do not do that. Think about it just on the design stage. Unfortunately, I know in reality, the people in charge of the design are probably not in charge of the use phase, and this is probably where the main problem is. And currently in a German committee for corrosion, we we are preparing a body of knowledge to think about what is really the competence an engineer should have in the field of corrosion protection in structural engineering. And think about it. If you have any feedback you want to give me regarding this particular point, you would be happy to consider it in our body of knowledge, because we think that corrosion is not sufficiently addressed in all the curricula and all the studies for structural engineering. And last but not least, I want to show you that I really did some inspections myself, and I did several, but I have only this particular photo where I did a bridge inspection in Florida. That's the reason why it was so hot. And on the right-hand side, this was the former chief of corrosion mitigation from the Florida Department of Transportation. And we had a lot of fun and a lot of sun when you do corrosion inspection in Florida. And I hope now that I'm still in time and that you have plenty of questions, and I will be happy to answer them.
Thank you very much, Sylvia, for a great presentation. I think you are in time. What we will do, I will remind everyone, if you would like to write your questions, these will be transferred to us. Before we start with the questions, allow me to mention that we would like to thank the University of Minho, the Federal Association of Concrete and Boutique Studios in Portugal for supporting this seminar series. And maybe to open the floor with a question, I would like to ask you, Sylvia, what do you think the role is of monitoring into this assessment process? Monitoring and maybe non-destructive evaluation. But if we think of monitoring as the situation where we try to continuously track with some means deteriorating processes, do you think there is room for that? Is this almost infeasible for the case of corrosion? What is your opinion?
We urgently need to apply it much often in field. The biggest issue with regard to corrosion monitoring is that we have this issue after 20, 30, 40 years in service, depending on the exposure condition. And normally the monitoring system itself does not survive 30 or 40 years. So we have to apply them later on. And here's the problem, because then we change the environment of the concrete and so on. There are solutions on the market, but the asset owners are a little bit doubtful to do so. We have 2 projects now going on where we would like to apply. We haven't done it yet, because since corrosion is a very dynamic mechanism, since it's dependent on the moisture condition, or the corrosion rate is dependent on the moisture condition, on the temperature and so on, we have seasonal development of the corrosion rate. But just by inspection, by testing, we do not gather just information we probably need in future in order to predict also the cracking due to corrosion.
Thank you for this reply. Maybe, I guess, to follow up with a question from the audience, or maybe first I give the floor to Maria Pina, who might also have a question as a co-moderator following the presentation. Maria Pina, you're
Sorry,
muted.
I
there
was
you go.
mute. Yes, I was mute. Thank you, Eleni. No, I was curious as well about monitoring. What for continuous monitoring, because you mentioned that there are sensors that can be installed embedded in the structure. But what kind of parameters do they measure? Is it possible to measure something in the passivation phase, or it's always when corrosion already is developed that information can be gathered?
We have several sensors available, which are also proven. For the initiation phase, we have sensors to monitor the chloride content, also in different depths, because we just want to know also what is the apparent diffusion coefficient for the concrete, and also what is the content, the chloride concentration, it's the level of the reinforcement. We also have sensors to monitor the pH, with a crucial parameter when it comes to carbonation-induced corrosion, just for the initiation phase. And as soon as we have to deal with, or if you want to decide if we are still in the initiation or in the propagation phase, so the potential of the reinforcement, the electrical potential of the reinforcement, we are also able to monitor And as soon as we know that corrosion is going on, here the corrosion rate is of particular importance, as well as the concrete resistance. This is more an indirect parameter. I would prefer always the corrosion rate itself as a direct parameter, but most often you have, it's only possible to measure the concrete resistance. But sensors are available. Not all of them are reliable and trustable. Some have some some techniques where I do not believe in. And I would always recommend to use the reinforcement itself as an electrode. Do not use auxiliary electrodes from somewhere from something which is totally different microstructure. It's not totally the same steel, because just from the formal production of steel, you have totally different electrochemical behavior.
Maybe there are questions from the audience.
Right. So let me transfer one question from the audience from Abraham Gedre. This question is on how, essentially, how to relate deterioration due to corrosion to a concrete computation of metrics, as for example, the reduction in the compressive strength of concrete. Which I guess pertains to ways of getting the information from data and then translating this into an analysis process.
I'm not sure if I understand the question accordingly. We still have a gap, because most the engineers doing the corrosion condition assessment are more from the material side. Sure, we have to work very closely together with the structural engineers. And for us, it's important to know what is really the information a structural engineer needs to know. You'll be happy to provide them this information. And what kind of structural assessment you have to do afterwards in order to get information about the reliability of your structure. This is something probably worth having an own presentation on.
Yes, my feeling as well is that this is not a trivial reply, but maybe we can point him to some of the literature and some of your literature, Sylvia, probably for this kind of calculation. Maria, I'm going to give it to you for the further question.
There is a question about post-tensioned bridge deck. When you have a situation with tendons with when you want to look for corrosion in tendons, which is likely to be localized, what could be a good way to detect this kind of corrosion?
This is a really, really good question where, unfortunately, I do not have such a good answer for, since normally, at least in Germany, it's often, the tendons are often protected in a tube. And then it's really the question, are you able to measure electrically through the tube? And we have a very dense, so we have a lot of tendons just beneath this other, so electrically connected. And it's quite, I would guess, I didn't evaluate the reliability of corrosion detection on tendons, but I would assume that it's very low without the potential measurements. And frankly speaking, I do not know what kind of method to recommend. You need to be sure, or to prevent corrosion, that there are no chloride ingress at all, and you need to be sure that you have how you call the material which is inserted in the tendons, that you do not have any cavities, any honeycombs, just in the tendon itself. That the tendon is totally protected. And normally you can check it with ultrasonics or radar, with any systems, that it's fully covered with the protective material.
Another question comes from Shubhra Maji, and it asks if you could comment on the extent to which non-electrochemical methods could be used to replace conventional, as he puts it, electrochemical methods.
It always depends what you like to know. If you really want to know about corrosion, which is an electrochemical process, the most reliable method is to apply an electrochemical method, which gives you a direct clue. I know that some of the publications try to show the applicability of some kind of wave-based methods in order to detect ongoing corrosion, but I still have my doubts, and also these methods are heavily involved by other factors such as moisture and so on. And since I have never seen the evaluation about the reliability of the test methods in order to detect corrosion, I still have my doubts.
I guess this is a comment more than a question from Jesus Rodriguez. Hi, Jesus, by the way. He says that from structural consequences due to corrosion, the loss of steel cross-section is the most relevant parameter in chloride attack, whereas bond decreasing and concrete spalling is quite relevant in carbonated concrete. Maybe if you want to comment on this comment.
Yeah, no, I understand. Normally what we see, it comes much faster, much easily to spalling when we have carbonation-induced corrosion. Then it's mostly a safety issue, and you have the loss of bond, and then we have to see if you have a compression zone or a tension zone, if you need the concrete or not. So we have here several dimensions we have to look at. And the issue is with chloride-induced corrosion, cracking, concrete cracking, very often does not appear. And we saw it on the case study here. The structure was very old with very high corrosion probability, and we saw that we had a lot of corrosion going on in the structure, but we had no crack at all. And so this is due to the fact that we have a different how you say, transport or diffusion characteristic of the iron oxides, which are produced due to chloride-induced corrosion, which can move much better in the concrete pore system. And here the pressure which is needed to lead to the cracking, it's mostly not high enough to induce the cracking. So I just want to say with chloride-induced corrosion, it's much, much later that you see the damage with visual inspection. And it's probably in line what the comment just wanted to mention.
Eleni, do you have other questions from the audience?
Yes, so there's one from Dave Whitmore. The question is, since corrosion potential is influenced by moist or wet conditions, what is the possibility that the assessment appears to be worse than it really is if the concrete is in humid condition? And he mentions that the use of corrosion rate measurements may be helpful when used in addition to corrosion potential measurements. What is your view on this, I guess?
Every information assists to give a full view on the corrosion assessment of your structure. It's totally right. The half-side potential measurement is dependent on the moisture condition of the concrete, but since we evaluate the results qualitatively to each other, then we need to ensure only that we compare these parts of the concrete which are in an equal moisture condition. If we have different moisture conditions on a structure, which could easily happen if some part is directly exposed to rain and the other not, we should not put all the potential data in one database and evaluate them. We need to to divide the structure with different moisture conditions, measure the half-side potential, and just make the evaluation particularly on the moisture condition. And as soon as you have additionally also the corrosion rate measurements together with your helpful foundation, this would decrease the uncertainty of your corrosion statement. Yes.
You mentioned uncertainty, and obviously now here we start discussing that, you know, the more information exists, the more helpful it is, and it can be heterogeneous information, right? Is there a good way to fuse all of this information, which eventually convert them into either different or one aggregated performance indicator?
Yes, not today, but we are working on that, and we are following a Bayesian, or we are at the moment developing a Bayesian network in order to get a performance indicator, which leads us to a key performance indicator. And here it's our aim in one project to evaluate just the effect of ongoing corrosion on the key performance indicator of reliability and safety. But we are not done yet with this task.
There was another question about which on the last part of your presentation, which was actually attracted also my attention, the comment that you said that more durable does not necessarily mean more sustainable. And there is a question from Juan who asks, do you have other specific examples? Because you showed an example of concrete cover with respect to cathodic protection. So do you have other examples which show this?
Yes, I haven't prepared a slide for this, but we have also, we did the evaluation comparing different kind of reinforcement. Even so, it is assumed that we always use carbon steel, but it's not necessarily the case. You could also use higher alloyed steel. But it was also for me a big surprise knowing that higher alloyed steels have a much worse environmental product declaration. So if you use much higher alloyed steel, it does not only increase your cost, but also the carbon footprint, because it is so bad, 7 times worse than carbon steel, high alloyed steel. And then you really have to think about, so your carbon footprint with carbon steel and with one repair is still less than building is with higher alloyed steel. As one of the examples, we are going to show these results today at 2 conferences, at the Concrete Solution and the ICC-RRR. And I hope that the steel industry will give us much better data, because it's very tough to get any data on the environmental product declaration, in order that perhaps we can strengthen the results.
And maybe one more question. Of course, you already mentioned this, and you mentioned the use of ultrasonics. But there is a question by Nze Rumia, if I say it correctly, on what is the potential of non-destructive methods, as for example, ground penetrating radar. So I interpret the question as to what is the potential of perhaps non-contact methods for assessment of corrosion.
Yes, we have. There are 2 points addressed here. One for the radar. I know there's some literature indicating that you can detect ongoing corrosion with radar, but it's also a very indirect measurement method, and I'm not really sure if it's just relied due to the that it's based on the production of iron oxides, which you're indicating or not. I didn't do any further studies by myself, but I have a lot of doubts. But there's also the possibility, or there's a patent to do a contactless corrosion detection by a means of the Kelvin probe application. It works. We validated it. This was just one of the pictures of the Florida Bridge, where we did some application study of a Kelvin probe device in order to detect corrosion, which is totally contactless. But unfortunately, we haven't found any company which is willing to build them and to bring it on the market. But we have this tool is available, and the patent is, and we have 2 patents on this device.
There is another question. If you can elaborate more on the corrosion assessment with probability models, because the comment is that half cell potential, how it can be used, because it is a thermodynamic parameters, whereas you are looking for corrosion rate. So if you can elaborate more on the use of this method for corrosion assessment and to integrate probability models.
Okay, I thought that I showed already such a case study where we used the half cell potential in order to get a probabilistic corrosion condition assessment. Even so, half cell potential is an indirect parameter, but as soon as we are able to detect corrosion current, this is just such a direct parameter, then we can show if we have a current, then we have corrosion, then it's 100%. So it's not very easy just to convert it in a probability statement. But I'm not sure if I got the question totally.
I don't know. Maybe because it's iPhone, so I don't know
Okay.
who asked this question.
Maybe the question was also about how you calculate, or the aspects that have to do with the probabilistic assessment. But I guess this was also part of what you briefly discussed.
Yeah, but we're working on Bayesian networks in order to increase the value of information from corrosion condition assessment. We're working on that to have a further probabilistic view, or more broader probabilistic view, not only considering, as I showed here, the half-cell potential data.
There is yeah, sorry, Eleni.
No,
go ahead. There is a question by Tadas who says that he heard that in Norway bridges are washed by water. Did you do any study to investigate if this is a good method and if it helps to reduce the corrosion, to, let's say, to delay the corrosion appearance?
What do they apply? I didn't get it.
Bridges are washed by water. Maybe you. I didn't know this method, so.
I do not know the method either.
So maybe Tadas, if you want to ask to specify your question, because maybe you have in mind a method that we are not familiar with it.
Maybe as we're on this topic, I mentioned a comment by Steinar Helland. He mentions that the simplest and most reliable instrumentation is to leave some rebar with half the specified cover. And I guess this is more of a brute force way to check if potential problems might arise there before it affects the main reinforcement. It's a valid comment, but that's also depending a lot on where this uncovered rebar exists, I guess. But I don't know, Sylvia, how you would think.
Yes, we have always high spatial variability, but I totally agree with Steiner. This is the best electrode you can have. Just the reinforcement is just the same material, which is embedded in the same concrete. So it gives you probably a very clear view. And we have also some sensors which just use this kind of electrode arrangement, I would say.
There is another question. Do you think that the linear potential resistance and potential dynamic potential or impedance spectroscopy measurements would be helpful in the calculation of corrosion probabilities?
Jein. Okay, now this is German expression. I know these are, I would say, more laboratory methods, which you're also able to apply on site, but these are very advanced technologies, and I would say not everyone is able to apply those. We only use them in lab, especially the electrochemical impedance spectroscopy. And it takes also very long. One particular measure can take 10 minutes, or depending on the settings, 20 minutes. And normally it's not the time you have on a structure. Definitively, this gives you very valuable information. But as I mentioned, the technology is so advanced, and the linear polarization resistance measurement, here you get only information about a spot. And here you have to really think about this could be used to prove these parts where you indicated by the half-cell potential measurement that you have a really high corrosion probability. But to do a scanning, I would say this is much too time consuming. It would be nice to have such data, definitively, but here we have to keep in mind that normally we have inspect those structures within 1 day. Or 1.5 days, you're limited to the downtimes of the structure, and you have to be fast. And this is the big advantage of the half-cell potential measurement method. You can do it relatively fast. You can scan it, and then you get a good overview about the whole structure in order to get an idea about the spatial variability of your corrosion damage.
Let me also transfer a comment and a question by Dave Whitmore. He mentions interesting data with regard to carbon footprint of repair with impressed current cathodic protection. And the comments you mentioned on the footprint of the electronics or the need for frequent replacement of these electronics. And I guess the question is, could galvanic cathodic protection be a much more low carbon footprint approach when used in combination with the repair?
Probably yes, even so we didn't do the assessment. Here I look always from the German perspective on the issue, and galvanic cathodic protection systems are not, not a favor because you cannot control it. Therefore, there are very, very few galvanic cathodic protection systems in Germany. But probably the carbon footprint will be reduced a lot because you need less electronics, yes.
Mm-hmm. Maria-Pina, any further question you wish?
I don't have other questions from the audience, if you have some.
Also on my side, I think we covered most of the main questions. And as we're nearing the end, maybe as we typically ask speakers, maybe Sylvia, you could leave us with the message on this theme that you would like to leave the audience with.
Okay, now a little bit unprepared, but nevertheless, I think what I tried to say during my talk is you need to consider corrosion just from the beginning. And even though you do not see it, does not mean that you do not have to care about it. Think about in which condition your structure is. And it's worth to apply some more advanced methods, not just visual inspection, to get to know more about your condition of your structures. And think about what is, for those who are teaching on structural engineering, what do we really think, or who's an asset owner, what do we really want to, what kind of competences you would like to have from the engineer, which is inspecting your structure, or which takes care about the structural reliability of the structure. Corrosion will always be an issue, and I was kind of surprised about the number of registration on this issue. At the beginning, I thought corrosion is such a kind of boring topic because we treated it for years, and I'm kind of surprised that this seems to be a blockbuster.
Yeah, it shows you that it's always a current or timely topic, obviously, so it's still critical. So I want to thank you very much, Sylvia. I think you covered it from several perspectives and also left room to think on what are next steps or future directions. Let me also say that we have a next EuroStruct seminar coming up in this same month in May 16th, with Alice Alipour from the University of Iowa, who will discuss a multi-scale approach to enhance resilience of infrastructure systems. You can check this as written in the chat in our main page, where you will also find recordings of this seminar, including the one from today. So I want to thank Maria-Pina and Sylvia again for the great discussions, and everyone who joined for attending this talk.
Thank you, Eleni. Thank you, Sylvia.
Have a nice day, everyone. Bye.
Bye. Bye-bye.